All right, let's start with A here. So this was the limit as h approaches 0 of h plus 2 cubed minus 8 over h. So on Monday, we looked at kind of techniques that would allow us to take limits without needing to do that kind of approach of just like plugging in values that are super, super close. We're going to find that that is particularly helpful on Friday once we actually start like doing stuff with derivatives in particular. But this is kind of working up towards that. What was the main technique that I said we could use like 99% of the time, almost always going to work, that would allow us to deal with cases like this where we're taking limits? Direct substitution, right? Most of the time, we would like to be able to plug in the value that we are taking the limit of. And as long as we don't get any domain issues, or as long as we don't have any weirdness going on with like piecewise functions, we should be in a pretty good spot. What's the issue in this particular case? We end up dividing by 0. Okay, so we can't use direct substitution as is, but if I can simplify this expression, I could then maybe use direct substitution. So that's kind of what we need to be looking at here is, can I simplify this expression in such a way that would allow me to use direct substitution? What can we do here then to simplify what we have? Well, we just said we can't do that because that would make us divide by 0. Say again? We'd have to multiply it on the bottom as well, and that's just going to like reintroduce it into the denominator. Ultimately, that is what we want to do. That is ultimately what we're going to try to do, is get that h to cancel by factoring out an h, which means we need to have a clearer vision of what's going on in the numerator, right? We would like to have an h in the numerator factored out that can cancel with the h that we have in the denominator. If it can't happen, then it can't happen. That is what it is. But that is kind of our goal here. Yeah, Hamza. Can we distribute that cubed? No, we can't distribute the cubed, but I like Hamza's idea here. I do want to simplify this part of the expression to see if we can't get anything going on. We can't distribute it because that would give me, you know, things to talk about with my therapist. But what can we do instead? Yeah, sure. Yeah. Yeah, absolutely. We could do h plus 2 times h plus 2 times h plus 2 and see what we get when we do this product. A little bit annoying. We have to do a 2 by 2 Punnett square and then a 2 by 3 Punnett square. But overall not too horrible. So H2, I get H squared, 2H, 2H, and 4. So this is H squared plus 4H plus 4 times H plus 2. And then doing the H squared, 4H, 4. With H and 2, I get H cubed, 4H squared, 2H squared, 8H, 4H, and 8, which means that I can rewrite this limit as the limit as h approaches 0 of h cubed plus 6h squared plus 12h plus 8 minus 8, all divided by h. What's going to simplify about this expression? 8 minus 8 will cancel. That's nice. So this is the same as the limit as h approaches 0 of h cubed plus 6h squared plus 12h all over h. And Harrison, what was your original suggestion here for how to deal with this h? If we can factor out an h, then the h on top and the h on bottom will cancel. And in this case, notice that we can, in fact, factor out an h. This is h times h squared plus 6h plus 12, which will let me cancel the h on top and bottom. This is the same as the limit as h approaches 0 of h squared plus 6h plus 12. Are we now running into any domain issues? No, we are not. And so what can we do to evaluate this limit? Just plug in 0, direct substitution. I get that this limit is 12. Questions with our kind of analytic approach for part A here? Yeah, Hamza. H. Yeah, that was the product at first. Other questions here? All right. Then let's take a look at B. Similar idea. Very similar idea. Like same problem actually, and you'll notice that the format that we see for A is very, very, very similar to the format that we see for B. That is not a coincidence. That is very much intentional. 2 plus h minus 1 over 2 over h. Again, what is the issue that we run into with trying to do direct substitution here? Dividing by 0, right? Zeros in the denominator are not going to be particularly kind to us. How then could I simplify the expression that I have here in order to maybe see, can we get this like h in the denominator to cancel? So we're going to run, if we multiply it into the top, we have to multiply it into the denominator as well. And then I'll just reintroduce it into the denominator. That makes sense. What's like not very simplified in this particular expression? Yeah, numerator is kind of a mess, right? I wouldn't give full credit for this answer at all. This is very much a mess. So let's try and clean that up. And maybe when we clean that up, it'll cancel with the h that we have in the denominator. So let's try that here. What do I need to do in order to subtract my fractions? I need to make sure that the denominators match. Is there a good, easy way to, through multiplication, make 2 match with 2 plus h? Not really. And so probably the easiest way to make this happen is let's just multiply both of the denominators together. So we'll multiply by a 2 over here on the left, and we'll multiply by a 2 plus h over here on the right. Probably the easiest way. Maybe not the only way, but I think this is a good one. In doing so, I get that this is the limit as h approaches 0 of 2 over 2 times 2 plus h minus 2 plus h over 2 times 2 plus h, all divided by h. We have to be a little bit careful here, just in that like this minus is applying to both the 2 and the h. So we want to be a little bit cautious about doing the subtraction. But when we do the subtraction, we get something very, very nice. This is going to be, so 2 minus, in parentheses, 2 plus h is negative h over 2 times 2 plus h divided by h. I'm going to go ahead just to make this next step a little bit nicer, a little bit cleaner, but it is h over 1. And of course, we're taking the limit as h approaches of that expression. In fact, maybe what I should do is maneuver this. Okay. So we have a fraction, we're dividing by something. What's maybe an easier way to do this rather than dividing by something? Multiply by the reciprocal. This is the limit as h approaches 0 of negative h over 2 times 2 plus h times 1 over h. And when we do this, what is going to happen? The h's cancel. We end up with the limit as h approaches 0 of negative 1 over 2 times 2 plus h. Are we running into any continuity errors or well, we're getting that to that today. Are we running into any domain errors here at 0 anymore now that the h is canceled? We shouldn't be. Maybe we still are. Again, that's certainly possible. But hopefully we shouldn't be. So what will direct substitution give us when we plug in 0 here? Negative 1/4. Very nice. Questions with our direct substitution kind of workarounds here for A and B? If, I don't know, hypothetically, we had like a quiz on Friday over this or something, these would be pretty good questions for that. How's this feel? So. Hopefully, most of it's just cleanup. Like a lot of it is just plug in as soon as we can. It's a little annoying when we can't immediately, but get some good practice in simplifying. All right, now let's take a look at C and D, which hopefully will be a little bit nicer. These should be a little bit more friendly. We are given a function, in this case, f of x, piecewise function. This is 3x plus 2 if x is less than or equal to 1 and it is x squared minus 1 if x is greater than 1. And the first thing we are trying to find is the limit as x approaches negative 2 of f of x. Now before, what we've kind of done with our piecewise is we've like looked at the top, seen what that's doing, looked at the bottom, seen what that's doing, looking at do they agree. We actually don't need to do that here. It's even simpler. If I am looking at what is going on around negative 2, which part of my piecewise function is the one that kind of governs what is happening in the vicinity of negative 2? Only the top. Whether I am slightly to the left of negative 2, whether I am slightly to the right of negative 2, it does not matter. I'm only using the 3x plus 2 definition when I'm in that vicinity. And so when I ask for the limit as x approaches negative 2 of f of x, this is the same as the limit as x approaches negative 2 of 3x plus 2. Does this have any domain issues? Certainly not. Definitely not around negative 2, but also just not in general. And so what is this limit going to be? It is negative 4. Doesn't even matter what the other function, what the other part of the function is doing. Okay. On the other hand, if we are looking at D, which is asking the limit as x approaches 1 of f of x, notice that around 1, we've got slightly different behavior, or vastly different behavior, on the left-hand side of this value and the right-hand side of this value. The limit as x approaches 1 for f of x, we have to split this apart into two separate limit statements. One that's looking at the left, one that's looking at the right. You could have done that for C. You don't really need to because you're going to be using the same function for both. And so we can kind of just get away with direct substitution. But here, because we are using different definitions on the left-hand side and the right-hand side, it would be wise to split them apart. Okay. Which function are we going to be using? Which definition? If I am to the left of 1. Top one, 3x plus 2. If I'm slightly to the left of 1, then I will be less than 1, 0.999999. And which definition will I use when I am slightly to the right of 1? The bottom one. Okay. Do either of these have domain issues? No. So what does direct substitution tell us about the left-hand limit? I think 5. Positive 1. Yeah, positive 1. And then what do we learn about our right-hand limit? Should it be -2? It should be -2, shouldn't it? Sorry. It would be 0 in the example that I gave. In this case, it was -2, negative 1. Regardless, though, what does this tell us about the overall limit? Because they disagree, the limit does not exist. Questions with our spell work here? No questions? All right, let's take a second to put our laptops up. We certainly do not need those out right now. And let's also take a moment to make sure that our phones are up right now.
Just save my Is the video from Monday up?
I don't think Mondays is yet. I'll do that this afternoon. Yeah, what's up? Yeah, go for it. All right. We are going to continue on to our next topic here, which is something that I've kind of been dancing around, trying to avoid using this word. Now we're going to put this to kind of put some terminology to some ideas that we have been talking about. I have mentioned that most of the time we can find limits using direct substitution. We have maybe some exceptions to that where maybe we have to do some finagling first to do direct substitution. But there is technically a quality of the limit that must be true, or of the function that must be true in order for us to actually use direct substitution. That gets into very circular definitions. So the way I characterized it was, if you don't have anything weird piecewise going on around the value, if you don't have any like division errors, dividing by zero errors, then you're probably going to be fine to just use direct substitution. If you can plug it in and not break math, you're probably okay to do so. We have words for that. And the word that we are going to use to describe this quality is continuity. So a function is continuous, or we have continuity. Casually, we can think of this as like the idea of an unbroken curve. That's fine. So for instance, this would be an example of a function that is continuous everywhere, right? There's not a single value of x for which we have like a break or a gap or a skip or anything. So this would be continuous everywhere. We could also have functions that are not continuous everywhere. So if we have discontinuous functions, would be functions where this is not the case. Do we have questions? Emmanuel, do you have a question? Okay, I really not have sidebars in the middle of lecture. So examples of discontinuities, we could have gaps in our function. We could have jumps in our function. And we could have, and we'll kind of put these to names, although the names here are actually pretty indicative. We could have some kind of like asymptotic behavior going on around certain values. Just some kind of skip in our function, some weirdness. Now, I do want to say it's really, really important to understand that when we are talking about continuity, we are talking about continuity at a particular value of x. So for instance, if the focus of my function is over here, then for our intents and purposes, this function is continuous on the interval that I have given. the function is continuous. For all the values of x that we see here, there are no skips, there are no jumps, there are no breaks. Whereas here, there's some funkiness going on. We've got some kind of gap, some kind of disagreement. Okay, so we're going to take this idea. We are going to put the kind of notions of this kind of graphical information, something that, like, if I presented you a picture, you could probably do a pretty good job of saying where discontinuities are. But let's actually put this into some kind of algebraic context with our limits. This is going to get a little bit jargony. But we'll look at some examples. We'll see, okay, this isn't actually so bad. And I'm going to try and give a very thorough breakdown of what this is even going to look like to like demonstrate that something like this is true. So a function, or maybe we'll say rather than a function, we'll say f of x is continuous at a if and only if, I denote with the if, the limit as x approaches a of f of x matches what we get when we just plug in a into our function. Which is kind of to say, like, if we can immediately do direct substitution with the point, then our function's continuous. Like the kind of the TLDR, although we have to be a little bit careful about that. Okay. So this actually ends up being a little more loaded in terms of showing that this bit is true than it would initially look. We can kind of break this process down into 3 separate steps of what we need to actually demonstrate in order to verify that this is the case. Yes, go for it. So step number 1, which is probably the easiest step, is to verify that f of a exists. Can I plug the value that I am focusing on into my function? So for instance, if we were looking at our bell work examples, can I, without any kind of an adjustment, amendment, or anything, can I plug 0 into these functions that I have here? No. Therefore, not continuous. Kind of. Well, we'll see that there's a little bit of an exception to these examples that we looked at, but that's fine. So if we can't actually plug in, then our function would not be continuous at that point. Okay. Example 2, or the second thing that we need to show. So if we confirm that f of a exists, we also need to show that the limit as x approaches a of f of x exists, which in and of itself requires us to show 2 things. What must we do to confirm that a limit exists? I have to show that that both sides agree. So we have to show that the limit as x approaches a from the left matches the limit as x approaches a from the right. Okay. And then the third thing is the actual thing that we're trying to demonstrate is that they match, right? That the limit that we have confirmed exists, in fact, matches the value that we get, the output that we get at A. Okay. Little jargony, I know. The if of stuff can maybe be a little intimidating. Questions just like conceptually before we take a look at an example? let's try this. Let's see what we've got going on here. So first and foremost, looking at example 1. So we are trying to verify if the function is continuous at the value that we have specified. We're going to look at 0, we're going to look at 2. Together, we're going to look at 2, and then I'm going to give you guys a chance to try with 0 to see if 0 is continuous. Okay, so we're going to do 2 together, and then I'll give you guys the chance to try at 0 yourself. Okay, what is the very first thing that we need to show in order to see if we have continuity? Okay, first we need to just plug in the point and see, like, do we get something that makes sense? Are we actually going to get an answer? Okay, if I am just plugging 2 into this function, which, if any, of these lines am I going to use? Which one cares about what is going on when x is equal to 2? Yeah, the 2 minus x1, this middle one right here. And how did we know that? The or equal to sign around that 2 is what's giving that one away. Okay. So f of 2, which in this case is 2 minus 2, which is 0. Is our function defined at that particular value? Yes. Okay. So we have confirmed that we have something going on there. Next thing we need to confirm is, does the limit exist? What do we need to do to show that the limit exists? Both sides agree. Okay, so we need to compare the limit as x approaches 2 from the left, and we need to compare the limit as x approaches 2 from the right. If I am using values that are slightly to the left of 2, which equation should I use? Yeah, we'll do the middle one again, right? We'll do 2 minus x. And is this limit one that is going to have domain errors at all? No. And so what do we get to do? Just plug in, and what do we get? 0. Nice. Okay. Which equation are we going to use for our right-hand limit if I'm looking at values that are slightly bigger than 2? Bottom equation. So this is x, this is the limit, I should say. As x approaches 2 from the right of x minus 2 squared. Do we run into any domain issues? No. And so what do we get to do? Just plug in. What do we get? Also 0. Do our limits agree? Yes, they do. And so our limit as x approaches 2 for this particular function exists and is 0. Final step, which we basically put all the work into anyway. Now it's just like making a statement, making a comparison. What's the thing that we actually are trying to show? Which is to say that what's true about the limit and our function at that point? They match. And so what we would say here is that the limit as x approaches 2 of our function is 0, which is the same thing as f of 2. Therefore, f of x is continuous at x equals 2. Questions with demonstrating continuity? How's this feel? Not too bad. Just kind of have to remember to show the things. All right, try it for 0. So at x equals 0. What's the first thing that we want to demonstrate? That'll be the second thing. So we'll do directional limits second. Very first thing, super quick check. What do we do first? Let's just like plug 0 into the function and see what happens. If I'm plugging 0 into my function, which of these 3 equations am I going to use? I'll use the first one because of that or equal to. So plugging in 0, I get 1. So does this exist? Yeah, it exists. Cool. Okay, now we're going to do our second check, which is directional limit. So we have the limit as x approaches 0 from the left, and we need to look at the limit as x approaches 0 from the right. Okay, if I'm looking at values that are a little bit less than 0, which function do I care about? Top one. Okay. And what happens? I guess the first thing I should say, can I do direct substitution with 1 plus x squared? Yeah, and what happens when I do? I get 1. Cool. Which equation do I care about when I am slightly to the right of 0? Middle? Yeah, the 2 minus x. Can I do direct substitution with 2 minus x? Certainly can. And what happens when I do? We get 2. What do we notice here? It is the limits don't agree, right? Notice that the left hand and right hand don't agree. Therefore, the limit does not exist. We have failed at step 2. Therefore, our function is not continuous or is discontinuous at x equals 0. Okay, quick thing that I want to address. Quick thing that I want to address, and that is we have some descriptors for types of continuity, different ways to be continuous. You'll notice there are several different ways that we can be continuous. We can classify discontinuities as removable, which we've seen before. We will also refer to these as holes. We could classify them as jump discontinuities, or we could classify them as infinite discontinuities, which we've actually also already seen before. These are vertical asymptotes. So of these examples that I have here, which one represents, we'll label these as like A, B, and C. Okay, go figure, no particular order. Which one represents a function with a hole in it? A, okay. If A is discontinuous, where is it failing? Which of my three conditions does it not meet? F of A doesn't exist. But notice that the limit does exist. If I were to take the limit as we approach this point, they do agree on the same value. It's just there's a gap there. There's just like a little point that's been removed, that's been kind of excised out. And so we run into holes. These occur when the limit exists. But f of A does not exist. Or we could run into a case where it exists, but it just disagrees, where f of A does not equal the limit. A way to do that, by the way, would be like if I just threw in a point like up here. Like it's a hole in my function. You could maybe make the argument that this should be a jump discontinuity. I think it's supposed to be classified as a hole. It doesn't really matter. But just this idea of the limit exists and the function is being argumentative, that means that we've got some kind of hole, something going on. Compare that to what we see for B, which would be our jump discontinuity. Why does B fail our continuity check? Both sides don't agree. Notice that my limit from the left and my limit from the right are giving me two different things. And so our jump discontinuity is going to arise when the limit as x approaches A from the left is not the same as the limit as x approaches A from the right. For instance, this discontinuity at 0 would be a jump discontinuity. From one side, we are approaching 1. From one side, we are approaching 2. That means that there's a big gap between the two right when we get to 0. We jump from one to the other. Yeah, here's. Yeah. Yes. No, you could have a floor function or a ceiling function where that happens. Okay. No. It's simple. It's simple. So if I define f of x as the floor of x, this is the way that you denote it. Then what this does is it takes whatever number you plug in and it rounds it down to the whole number version. So for instance, f of 2.863 is going to be just 2. It rounds it down to the nearest whole number. F of 3.999 is just rounded down to 3. Yeah, you get like gaps. You get like, I'm gonna have like this, and then I like jump, and then I get this, and then I like jump. You get this like stepwise kind of function. But that would be a pretty bizarre case. The ceiling function does the same thing, but it rounds everything up. And you get the same shape. But most of the time, yes, they like it. But most of the time, the jump discontinuities are only going to come from piecewise functions. This might be the only example that I could come up with where it's not. Good question. I think there actually is, I think there is an example on the classwork that's doing that shape, and it's either a floor or a ceiling function. Yeah. Okay, and then an infinite discontinuity. An infinite discontinuity is going to have, it actually fails in a couple of different directions. But importantly, it's that the limit as x is approaching a value from either the left or the right is going to give you plus or minus infinity. Technically, you could say that means does not exist. We'll explore that a little bit more tomorrow. No, quiz on Friday. If hypothetically we had a quiz on Friday. But like also we've already seen holes and asymptotes before. They're doing the things that we expect them to. Okay, questions with definitions here. Okay, one more example that I would like to look at. If you were, I'm sorry, Will, but if you were planning on doing tutoring this afternoon, I'm not able to do it anymore. Got an emergency text. But I will. I don't know. This week's kind of crazy. So no tutoring this afternoon. But we'll figure out your thing later.
Thursday.
We'll see. I might not be able to. No, I can do Thursday. We can do tomorrow. Yeah. Okay. Let's take a look at example 2 here. Similar kind of question. These are fun ones. And we'll look at a couple that are interesting here. So we are trying to find the value of c such that our function is continuous for all values of x. All right. One thing that I would like to note, and I mentioned this earlier, but I want to write it down. It would be a good thing to write down in your notes, which is that if we can use direct substitution, essentially like immediately, like without any kind of modifications, then the function's going to be continuous. So if direct substitution makes sense, which remember, as long as there's no piecewise weirdness, as long as there's no like dividing by 0 error going on, then we can probably do direct substitution. If we can, then it's going to be continuous. So for instance, taking a look at example 2a here, let's consider kind of 3 different classes of number. We have numbers where I'm only going to be using the top equation. We have numbers where I'm only going to be using the bottom equation. We have numbers where maybe I have to consider what's going on with both. For numbers that are less than 2, where I do not care what's going on with my bottom equation, so c x squared plus 2x, are there any values of x where I am potentially running into a domain error? Are there any values of x that I couldn't handle using direct substitution? No. And so what we can say here is that for any value of x that is to the left of 2, anything less than 2, our function is going to be continuous. We can just do direct substitution. We'll be fine. What about everything to the right of 2? If I'm only looking at x cubed minus cx, are there any values of this particular function where I have to worry about like discontinuities, anything like that? No. Right? C is just a number. C could be like 4, right? Just some number. But we don't have to worry about dividing by 0. We're not worrying about square roots of negatives. In fact, we're basically not doing that for any of these. As long as I'm bigger than 2, I am also going to be able to use direct substitution instantly. If I'm able to use direct substitution instantly, I'm good to go. What then is the only value that I actually have to worry about? The only value that I actually have to worry about is what is going on at 2. That's it. That's all we need to worry about. So let's do our continuity check for what is going on at 2. And we need to find a value of C that will work for 2 here. So let's try this. So this is, we'll go through our list here. What is the very first thing that we need to show that something is continuous? Okay, so first thing we need to do is show that f of a exists. We are caring only about what is going on at 2. What is f of 2 in this case? Eight minus 2c is replacing the x's. Perfect. Regardless of what value I pick for c, is this going to exist? Yeah. C is irrelevant. That's certainly going to exist. We'll like check in with that value of C here in just a moment and see kind of what's going on. Okay. What is the second thing? And this will be the important one. What is the second thing that we need to check if our 2 sides match? So in this case, we need to say what is going on as we approach 2 from the left, and we need that to be the same as what is going on as we approach 2 from the right. We're not trying to confirm, is this the same? We're trying to find a value of C that makes this work. In this case, if we are looking at what is going on to the left of 2, which function should I use? We'll use the top one, the cx squared. So this is the limit as x approaches 2 from the left of cx squared plus 2x. And that needs to match. Well, first of all, what is that? Let's evaluate that first. Four c plus 4. I agree. Just plugging in 2. And that needs to be the same as the limit as x approaches 2 from the right of which function am I going to use? Bottom one of x cubed minus cx, which, what is this when I do my direct substitution? 8 minus 2c. Subtracting 4 from both sides. Thank you. Subtracting 4 from both sides. Adding the 2c over dividing everything by 6. I get that c must be 2/3. So if c is 2/3, then my limits are going to agree. Okay, technically speaking, we do have one more thing that we should show to confirm that it is, in fact, continuous. So we've shown that the function exists at that point. We've shown that the limit exists as long as c is equal to 2/3. What's the last thing that we need to demonstrate? So we've shown everything exists. Cool. We have to show that, do they match? This is going to be kind of trivial for this particular problem, but I will go through like just a quick rough process of it. The way that we can know that they match, the brute force way would just be to plug 2/3 in for C and show like, do they match? Easier than that though, is to say that f of 2 should just be the same as the limit as x approaches 2 from the right of f of x. Can we agree with that? Plugging 2 into the bottom equation is the same as taking the right-handed limit of this function. Those should match. That feel like a safe thing to say? Okay. And we know that the right-handed limit is just the same as the overall limit since the limit exists. So the limit as x approaches 2 from the right is just the same as the overall limit. And so if our function at 2 matches the right-hand limit, then it must also match the overall limit. Transitive property of equality, if A equals B and B equals C, then A must equal C as well. So that's just like extra dotting our I's and crossing our T's kind of bits. You could probably be done as soon as you have found that C is 2/3, but if you wanted to be extra, extra, extra good, then that is what you would want to do. All right, questions with continuity? All right, we'll call it there. We've got about 7 minutes left. The classwork due Thursday night. And you guys have the rest of this time to work on it. Yeah. Yeah, absolutely. Give me one. Yeah, of course. Grab the